Dr. StrangeLOVE, or How I Learned to Stop Worrying and Love Omitted Variables. A chapter in Lance and Vandenberg's Statistical and Methodological Myths and Urban Legends. Dr. StrangeLOVE, or How I Learned to Stop Worrying and Love Omitted Variables, by Mead, Behrand, and Lance. A well-known problem in path analysis and structural equation modeling is that even the largest and most comprehensive models cannot contain all of the causes of models' endogenous variables. This violation of one of the underlying assumptions of path analysis and SEM gives rise to a commonly held belief that failure to include all relevant causes of endogenous variables may invalidate study results in path analysis and SEM. This problem has been referred to variously as the unmeasured variables problem, the omitted variables problem, left out variables error, or LOVE, a lack of perfect isolation, lack of self-containment. It has also been discussed as a particular type of model specification error. The omitted variables problem arises when the assumption that all relevant variables that influence the dependent or endogenous variables are included in the model is violated. However, in the social sciences, this assumption is rarely, if ever, fulfilled. Although there is no shortage of scholarly discussion and writing related to omitted variables, it is less clear how often this issue arises in substantial academic and applied research. This is because discussion of omitted variables usually takes place behind the scenes. For example, during the manuscript review process. In response to a post to the RMNet message board on June 11, 2007, several authors indicated that omitted variable discussions have arisen during the review process. In one example, an anonymous reviewer commented on a paper related to sources of work absenteeism. However, omitted variables that are tied to absenteeism still remain a concern of family size. Number of children and being single head of household are also related to race/ethnicity. This issue is not that perceived value of diversity in children, etc. are related, as the authors contend. It is that race is correlated with both reports of value of diversity and number of children, etc., and then with absenteeism. Hence, absenteeism is potentially being driven by factors other than what the authors allege. Simply acknowledging the lack of critical data does not eliminate the concern that major confounds were not adequately controlled. This comment is undoubtedly typical of those researchers regularly encounter. In order to provide some index of the extent to which researchers considered omitted variables in their work, we conducted a cited reference search. Specifically, we used the Social Science Citation Index to identify works that cited two seminal papers on omitted variables, James 1980 and Mauro 1990, on the assumption that authors dealing with omitted variables issues in their research would be likely to cite these works. A total of 63 sources were found that cited these studies. We then coded each of these sources into one of four categories based on the context in which they discussed omitted variables. Of the 63 sources, 12 actually took steps to assess risk from omitted variables or acted to minimize the impact of omitted variables in some way. Including relevant variables not of central focus to the model, testing alternative models with and without potential additional determinant variables. An additional 21 articles cited James or Mauro 1990 when discussing the potential biasing effect of omitted variables, but did not attempt to account for such variables in any way. 26 sources cited these works as part of a methodological review of path analysis or SEM. Finally, 4 sources mentioned the potential of omitted variables as a limitation of previous research in order to help justify their current study. In some, it seems that reviewers and others critically evaluating organizational research are aware of the omitted variables issue and voice concerns over love, perhaps even in contexts in which there is minimal risk of omitted variables compromising research conclusions. On the other hand, authors seem to address omitted variables in a meaningful way less frequently than would be desired. This is not surprising, given that authors may not want to call attention to methodological issues that could question the validity of their study conclusions. However, there are some instances in which omitted variables do pose a considerable threat to the conclusions of path analysis and SEM. In order to provide a better understanding of when omitted variables may or may not jeopardize the validity of path analysis and SEM, this chapter has 3 goals. A. Review the relevant assumptions in path analysis and SEM and present a mathematical explanation of the omitted variables problem. Discuss the conditions under which omitted variables are likely to be problematic and those under which the effects of omitted variables are negligible, and provide recommendations for minimizing the risk of love. Theoretical and mathematical definition of the omitted variables problem. Conceptually, the problems that may be caused by omitted variables are not difficult to understand. When researchers specify path or structural equation models in order to evaluate a theory, path coefficients are estimated based on the correlations among the measured variables in the model and the pattern of structural relations specified. If an endogenous or dependent variable is affected by a variable that is unmeasured, and the unmeasured variable correlates to a moderate degree with other causal determinants in the model, the effects of the unmeasured variable can be incorrectly attributed to the measured causal determinants in the model, while the effect of the omitted variable could serve to decrease the magnitude of the path coefficient of the measured variable, that is, a suppressor effect. It is more often assumed that the effect would cause a positive bias in the path coefficient of the measured variable, while the effect of the omitted variable could serve to decrease the magnitude of the path coefficient of the measured variable, that is, a suppressor effect. It is more often assumed that the effect would cause a positive bias in the path coefficient of the measured variable. This positive bias could also result in the determination that a determinant has a statistically significant effect on an endogenous variable when such a finding would not have been the case if the unmeasured variable had been included in the math model. This error is referred to as love. The omitted variables problem is perhaps best understood by first looking at the basic mathematics supporting path modeling. In order to clearly demonstrate this issue, we outline a series of progressively more complex path models based on standardized variables. That is, beta will be used as the symbol for path coefficients and regression weights. These models may then be generalized to the case of latent variables in SEM as the underlying conceptual issues are the same. The simplest linear causal model includes one exogenous variable, x, and a simple single endogenous variable, y. Assuming that both are expressed in standard score form, the relationship between them can be expressed as follows. Y equals to the product between the standardized regression coefficient corresponding to x multiplied by x plus d, which is an error term, also known as a disturbance term, where beta yx is the standardized regression coefficient, d is a disturbance term composed of random shocks, non-systematic measurement error, and unmeasured relevant causes, and unmeasurement non-relevant causes. Random shocks can be thought of as unstable causal influences. Measurement error refers to non-systematic error, and unmeasured causes are omitted variables. Whether or not a cause is relevant depends on the nature of its relationship with other variables in the model and is illustrated below. Figure 4.1 illustrates the path model for the case of a single causal exogenous variable and a single endogenous variable. In Figure 4.1a, the disturbance term consists exclusively of random shocks, measurement error, and unmeasured non-relevant causes. For this model, the expected relationship between x and y is given by the equation the error of x product y equals to beta yx multiplied by the error of the product between y and y plus the error of the product between x and disturbance. For Figure 4.1a, e x asterisk y reduces the byx as e y asterisk y equals to 1 for standardized variables, and the error x asterisk d equals to 0 because the expected relationship between each of the three components of d, random shocks, measurement error, non-relevant causes, and x equals 0. In this case, the correlation between x and y is an unbiased estimate of the causal parameter of beta. In figure 4.1b, however, an additional component is present in a disturbance term, an omitted relevant cause, O. As before, the expected relationship between the random shocks, measurement error, and non-relevant causes and x equals 0. However, the expected relationship between x and d equals to rb beta, as there is an indirect effect of x on d due to the omitted variable that is present in d. An important concept to highlight is that the relevance of an omitted determinant of the endogenous variable is based entirely on the omitted variable's relationship with other variables in a model. That is, if the omitted causal variable correlates with other determinants of y, the omitted variable is by definition a relevant omitted variable. Conversely, if the omitted variable does not correlate with other determinants of y, it is by definition a non-relevant cause of y. Consider now the case of a path model in which one of two exogenous variables is erroneously omitted from the path model, O, in figure 4.2. Assume further that O correlates significantly with both x and y. In this case, the measured correlation between x and y reflects not only the direct effect of x and y, but also the indirect effect of x and y via the shared correlation both variables have with O. In other words, the observed correlation is determined by the following equation. However, because O is omitted from the path model, the naively estimated path between x and y will be equal to the correlation between y and x, though the correlation between y and x is actually determined by the effect of both the regression coefficient corresponding to x to y, as well as the correlation between the path coefficient from the omitted cause to x and the regression coefficient corresponding to the relationship between the omitted variable and y. As a result, ryx as an estimate of byx will be biased by a factor of rxo beta yo. The effect of rxo is obvious. If x were not correlated with O, then ryx is not affected by O, and ryx is an unbiased estimate of byx. In this case, O is a non-relevant omitted cause of y. That is, its omission from the path equation has minimal effects on the estimated path coefficient of the included exogenous variables or on their associated test of statistical significance. Conversely, if x were non-trivially correlated with O, rxy would differ from bxy by a factor equal to rxo beta yo, so that rxy would be a bias estimate of beta xy. This bias can affect tests of statistical significance and lead to erroneous conclusions regarding the model. In this case, O is a relevant omitted cause of y. Although the potential biasing effect of rxo on beta yx is obvious, the effect of byo is less transparent. The equation for the path coefficient of beta yo is as follows. So that in order for beta yo to have a biasing effect on the correlation between x and y, which could be taken as the estimate of beta yx, the correlation between x and O must be non-zero. If the correlation between x and O is non-trivially positive, bias in beta yx will be greater when the correlation between y and O is large and the correlation between y and x is small. In order to provide some context for illustration, Table 4.1 includes several hypothetical values for rxy, rxo, ryo. Note that no values of rxo equals to 0 are presented because there is no bias in rxy as an estimate of beta yx, when there is no correlation between the exogenous variable and the omitted variable, that is, O is a non-relevant cause of y. As can be seen in Table 4.1, bias is greatest when the correlation between x and y is somewhat low, yet the omitted variable correlates highly with both x and y. This is the classic third variable problem, the spurious correlation between ice cream sales and drowning deaths. And a primary reason this correlation cannot be interpreted as causation. In this case, much of the effect attributed to the relationship between x and y is actually due to their mutual correlation with and/or dependence on O. Note that when the correlation between the endogenous variable and the omitted variable is close to 0, beta yo can take on negative values. When beta yo is negative, rxy, which is used to estimate beta yx, is mathematically equal to beta yx plus the product between rxo and beta yo, will actually be greater than beta yx. In this case, the omission of O causes an underestimate of the path coefficient between x and y, and variable O is said to have a suppressor effect such that its inclusion in the model serves to increase the estimated path coefficient between x and y. Examples of such negative bias are present in Table 4.1. Suppressor effects are most readily manifested when the omitted variable has a very low correlation with the endogenous variable, but a moderate or large correlation with the exogenous variable in question. In such cases, the true path coefficient for the observed exogenous variable is considerably larger than the zero-order correlation between the exogenous variable and endogenous variable that is used as an estimate of the path coefficient. In sum, several important points result in the discussion of a model with one observed determinant and one omitted determinant of a single endogenous variable. The correlation between x and y will be a biased estimate of the path coefficients of y from x to the extent that there exist omitted relevant causes of y. This bias will be upward, that is, the true relationship is actually greater than that which is represented by the regression coefficient, to the extent that the relationship between measured and omitted and multiplied by the relationship between the criterion and omitted is greater than 0. By extension, both rxo and beta yo must be non-zero for bias to occur. If either rxo is close to 0 or by0 is close to 0, no bias occurs. If one of the terms is negative and the other is positive, a suppression situation occurs. If rxo and beta yo are both negative, there will be upward bias in the estimation of byx from rxy. Violated assumptions. Omitted relevant variable represents a violation of the assumption of self-containment in causal modeling, and is but one type of model misspecification. We cannot isolate an endogenous variable from all potential causal explanatory variables in the social sciences. Instead, we replace the assumption of isolation with one of pseudo-isolation by assuming that the disturbance term, variance in the endogenous variable not accounted for by its model causes, is uncorrelated with exogenous variables, or with endogenous variables that precede the variable in question in the causal path. This can be seen again by examining Figure 4.2b. In Figure 4.2b, the disturbance term, d, would now include the effect of the standardized omitted variable, beta yo. Clearly, the self-containment assumption is violated, as x will correlate with the disturbance term by a magnitude equivalent to the product between rxo and beta oy. More complex models. Although the effects of the omitted variable are clearly visible in a model with two exogenous variables, things rapidly become more complex when more variables are added to the model. Figure 4.3 depicts a path model illustrating the partially mediating effect of a mediator on the relationship between an exogenous variable x and an omitted relevant causal variable O, with the endogenous variable y. The path model for M is identical to that of a two exogenous variable model. As in the previous example, if O is omitted, then the expected path coefficients and potential for bias are identical to those of a path coefficient with two determinants. There are three causes of y, yet one of these is omitted. The true population path equation for this model is as follows, and the path coefficient beta yx in the true model is given as follows. More complicated models are obviously possible as well, though algebraic expressions for the path coefficients rapidly become unwieldy. In the current example, a variable O were omitted, the estimated path coefficient for the direct effect of x on y would be that of a two-determinant model, in which the effect of the omitted variable is ignored. In order to further illustrate the effects of an omitted variable in this model, data were simulated for several levels of correlation between variables O and y. Table 4.2 contains the level of bias observed in the path coefficient of x for different levels of correlation between the omitted variable and the other causal variables in the model. Readily apparent from Table 4.2 is that the magnitude of bias is not large in any of the conditions when the correlation between O and y is 0.20. Results are more mixed for those correlations in which the correlation between the omitted variable and y is 0.60. In these conditions, the magnitude of the bias of path coefficient of x can be large, but only when the correlation between the x and O is also quite large. Interesting interaction effect. Also, the magnitude of the bias is mitigated somewhat by the correlation between omitted variable and m, though the bias is still sizable. Note the values presented in Table 4.2 that represent the case in which there is a relatively small correlation between x and y, and large correlations between O and both y and x. Under these circumstances, bias can be sizable. We set the correlations in Tables 4.1 and 4.2 to arbitrary values in order to demonstrate their effects, but in practice, correlation coefficients may not plausibly vary independently of one another. In other words, a situation in which two variables correlate very highly and one of those two correlates highly with the third variable while the other correlates negatively with the third variable is mathematically improbable. The patterns of correlations that result in the most bias are those in which there is a very low correlation between the measured determinants and the endogenous variable, and high correlation between both the measured determinants and omitted variables and the omitted and endogenous variables. While such patterns of correlation are mathematically possible, they may be unlikely in some domains of study, given what is known from previous research. To summarize, omitted variables can introduce bias in estimated path coefficients, and this bias may be positive or negative in direction. The issue is, then, under which conditions is it possible for an omitted variable to bias path coefficients? Below is a summary for a model with one observed exogenous variable and one relevant omitted variable. If O is uncorrelated with the exogenous variable, the correlation between x and y is an unbiased estimator of the path coefficient of y from x, and the omitted variable has no effect. If the variance in y accounted for by O is completely redundant with the variables in the model, its unique effect, that is, the path coefficient of y from O, will be near zero and will have little biasing effect. If O is uncorrelated with the endogenous variable, but strongly correlated with the exogenous variable, the correlation between x and y may underestimate the true path coefficient of y from x, that is, a suppressor effect. Thus, there are three conditions which must be present in order for an omitted variable to cause positive bias in estimated path coefficients. The variable has to correlate at a non-zero level with other determinants of y, not be completely redundant with other variables included in the path model, and correlate with the endogenous variable. If A and B are true, but C is not, the omitted variable may serve to artificially deflate the estimate of the path coefficient of the variables included in the model. In sum, the potential for love, or lack omitted variable error, I think, lacking omitted variable error, is greatest when the omitted variable correlates highly with the outcome variable and moderately with other determinants in the model. Path coefficient bias versus significance testing. It is important to make a distinction between the biasing effect of omitted variables on the magnitude of path coefficients and the effect of omitted variables on the significance test of those path coefficients. Generally speaking, in theory building via path analysis and SEM, there are two important outcomes of interest to the researcher. The magnitudes of the estimates of the path coefficients themselves and associated significance tests. Often, in early stages of research, the primary outcome of interest in path analyses is the significance test associated with the path coefficient. In other words, the answer to the question, does the variable have a unique effect on the outcome, would seem more important than the question, what is the precise magnitude of the unique effect of the variable on the outcome? If early forays into model testing with a given set of variables indicate that the effective determinant on an endogenous variable is non-significant, it is less likely that future researchers would include this variable as a measured cause as frequently as if the variable did have a significant effect on the outcome. In this context, the magnitude of the path coefficient per se is less important than the decision as to the presence or absence of an effect of x and y. If there does appear to be an effect, that is, the test is significant, then future use and, importantly, replication of this effect is much more likely. While the rough magnitude of this effect is undoubtedly important, small bias in the path coefficients would likely be of little concern so long as the conclusion of the significance test is not affected at this stage of investigation. The second outcome of path analysis is the magnitude of the path coefficients themselves. Estimates of path coefficients are important in that standardized coefficients are one index of the unique variance in the endogenous variable accounted for by the determinant. Additionally, unstandardized coefficients can be compared over time, and cumulative evidence can be collected such that the relative effect of determinant on an outcome can be estimated. As research accumulates over time, the precision of estimated paths becomes important to future meta-analysts, such that an accurate estimate of the effective determinant on an endogenous variable can be calculated. Thus, even though precise estimates of effects may not be of primary interest to a researcher in early stages of research on a topic, these estimates take on additional importance over time as research accumulates and meta-analyses are conducted. Recall that if the omitted variable does not correlate with the endogenous variable, but correlates with other variables in a model, it may act as a suppressor variable. This was shown in tables 4.1 and 4.2, where the exclusion of an omitted variable resulted in a negative bias of the estimated path coefficients. That is, its inclusion in the model could serve to increase the estimated path coefficients of the observed variables. In regard to significance testing, omitted variables that do not correlate with the endogenous are potentially problematic in that they may result in type 2 errors, that is, failure to detect an effect that truly exists. However, reviewer criticisms of a lack of comprehensive path models typically center more on the potential upward biasing effects of omitted variables and associated type 1 error, that is, wrongly identifying an effect that does not exist. The focus on type 1 errors is understandable, as such errors may translate to immediate implications for practice in the use of an determinant variable, whereas type 2 errors are less likely to be published and likely will be rectified in future studies. If type 2 error is seen as less problematic as type 1 error, the requirement of a significant correlation between the omitted variable and the outcome may be added to the list of conditions that must be met before the possibility of an omitted variable becomes a concern in path models. Omitted variables that do not correlate with the outcome cannot cause upward bias in path coefficient estimates. Let me repeat that again. Omitted variables that do not correlate with the outcome cannot cause upward bias in path coefficient estimates, which is typically the focus of LOVE concerns, minimizing the risk of love. There are specific conditions under which omitted variables can be problematic, and it is true that no matter how comprehensive a path model, there are always omitted relevant variables in organizational research. We have also illustrated that there can be substantial bias under some conditions. Thus, there is a kernel of truth relating to love in organizational research. To this extent, educating researchers on the ways in which to minimize the risk of omitted variable problems is of paramount importance. There are several ways in which organizational researchers can minimize the risk of omitted variables biasing path coefficients discussed below. The first is experimental control. First, one could incorporate design characteristics that minimize the correlation between measured exogenous variables and omitted variables. Random assignment of participants is extremely successful in controlling for a wide range of known or unknown omitted individual difference variables. As we have emphasized, there can be no possible biasing effect of an omitted variable if that variable does not correlate with the observed variables in a model. As such, random assignment is highly effective for controlling for almost any individual difference variable in a path model. Although random assignment may not be possible in many instances of organizational research, there are some causes in which it may be employed. For example, participants may be randomly assigned to different types of training courses, reward systems, equipment, and in other environmental factors or organizational interventions for which the effectiveness may be evaluated. In more mathematical terms, recall that in the case of one exogenous variable x and one omitted variable O, the estimated effect of x on the endogenous variable y is the zero-order correlation between x and y. However, the true effect of x and y should be given as equation 4.8. When random assignment is used, the correlation between x and O will be near zero with sufficient sample size. Thus, equation 4.8 reduces to Rxy and there is no bias. More inclusive models. Second, researchers should include as many known causes of the endogenous variable as is practically possible in the path model. The potential for bias in path coefficient estimates caused by omitted variables is much greater when they serve as unique causal agents of the endogenous variable. Recall that for a two-determinant model with one determinant omitted, the bias present is equal to the product between the correlation between the predictor and the omitted determinant multiplied by the regression path coefficient between of the criterion from the omitted variable. By incorporating more determinants of the outcome, the unique effects of omitted variables may be reduced as beta y(O) approaches zero. Note, however, that there is a paradoxical side effect of including more variables. That is, each additional determinant that is included in the model is also prone to love and is subject to the assumption of model self-containment, using previous research to justify assumptions. Researchers may also use what is already known from past research to demonstrate that omitted variables are not likely to be problematic. For example, when estimating the effects of ability determinants of job performance, one can legitimately leave out entire classes of other performance determinants, such as personality and motivation, because they are likely to be uncorrelated with ability determinants, and therefore are non-relevant causes. On the other hand, if both verbal and quantitative aptitude were thought to be causes of job performance, it is unlikely that the omission of similar types of tests, for example, mechanical ability, would produce a strong biasing effect on path coefficients of those tests in the model, as mechanical ability is exceedingly likely to have a large correlation, that is, be redundant with, the measured ability test variables. As such, the plausibility of bias due to omitting mechanical ability tests is very low, as again, beta y(O) will be closer to zero. Put differently, in many instances, non-relevant causes can largely be ignored because they are either A, not related to measured causes, or B, largely redundant with relevant causes that are already measured. To this extent, prior research on correlates of both the outcome and other determinants can provide guidance on what variables are essential to include in a model and which may be safely omitted. Consideration of research purpose. If the goal is to provide a precise estimate of path coefficients or to compare the relative variance accounted for by different determinants, omitted variables are considered more problematic than if the goal is to test the statistical significance of the effective determinant on an outcome. Examining again the simple two-determinant case, Influence due to omitted variables can result in bias in the estimated path coefficient with respect to its true value. However, with large sample sizes, even sizable bias in estimated path coefficients are less likely to change decisions drawn from the statistical significance test associated with these conditions. With larger sample sizes, power is such that even small estimated effects tend to be statistically significant. In sum, omitted variables are a fact of life in organizational research, and they can be problematic. Researchers should be particularly vigilant in cases in which A. there are a large number of determinants of the outcome variable, B. the study in question includes only a small subset of those determinants, C. it is likely that the omitted variables have moderate or large correlations with the measured determinants, and D. it is likely that the omitted variables would account for unique variance in the outcome variables. However, the notion that omitted variables are always problematic is a myth, as the threat to the inferences that we tend to draw may not be as serious as some have believed.